Here is something most people who do not work in chips do not know. On a modern 3-nanometer system on chip, finding the bugs costs more than designing the chip in the first place. 60% of the engineering hours on the program, half of the silicon's total mass set risk, 80% of the compute bill on the cloud. The bill is in the hundreds of millions of dollars per advanced program, and it is getting worse, not better. AI tools are arriving for chip verification right now, and every one of them generates more tests, more coverage targets, more scenarios to chase. The compute bill goes up, the number of bugs an engineer must triage goes up, and the cost of an escaped bug, the one that slips past every test and lands in silicon, is still $20 million in mass cost and a quarter of program calendar. This is a story about the people who hunt those bugs, what their job actually looks like at 3 nanometers in 2027, and which two industries in the entire compute stack profit most when AI helps verification turns into a budget line. The answer at the end is not the EDA vendor by itself. The design verification engineer, the DV engineer, is the person who proves the chip will do what the spec says before it goes to TSMC, not by simulating the geometry like the physical design team, by simulating the behavior. Billions of clock cycles, every register, every memory transaction, every interrupt, every corner case the architecture team can imagine, and 1,000 more the DV team has to imagine on their behalf. On a modern AI accelerator program, the DV team is typically larger than the design team, 2 to 3 DV engineers for every 1 RTL designer, and 4 hard things define the role. 1, turning an English language specification into an executable check. 2, deciding what coverage actually means and when there is enough of it. 3, when a regression fails, triaging which of 5 possible root causes is the real one. 4, deciding when simulation is too slow to finish in time and the program has to spend $10 million on an emulator. Each one is a place AI tools cannot carry the work alone. Walk through them. The first wall is the spec. The architecture team writes a Word document, a few hundred pages, state machines drawn as boxes and arrows, memory ordering rules described in English sentences, power down sequences explained as bullet lists. The DV engineer's job is to turn every one of those sentences into a SystemVerilog assertion or a UVM test sequence that the simulator can actually check. The translation is never one-to-one. The spec says the cache must complete write-back before the bus transaction commits. But what counts as completion? When the last data beat leaves the buffer, or when the destination acknowledges? In which clock domain? Under which power state? The architect knew what they meant when they wrote it. The document might not. Synopsys VC AI and Cadence Verisium can auto-generate test sequences from an existing test bench. They cannot read intent out of an ambiguous paragraph. The DV engineer walks to the architect's desk, asks the question, comes back, writes the assertion, runs it, finds the case where the RTL designer interpreted the sentence differently. That is a bug found before silicon. A model can suggest tests. It cannot decide what correct looks like. The second wall is coverage. After the test bench is written, the regression runs for a week on 1,000 cloud cores. 500 million clock cycles per nightly run. The coverage report comes back with a number. 98%. The DV team leader looks at the number and asks the question that decides whether silicon ships on time. Is 98% enough? It depends on what the 2% is. Code coverage just measures whether lines of RTL got executed. Functional coverage measures whether scenarios got exercised. Cross-coverage measures whether scenario combinations got exercised. The bug that kills a tape out is almost always at an intersection, cache in a specific state, while the bus is stalled, while an interrupt arrives, while the security mode is transitioning. 3 independent conditions, each rare on its own, and their product is the bug. The simulator can run 1 billion cycles and never construct that intersection unless the test scenario was written to construct it. AI coverage tools can suggest new test stimuli. They cannot tell you which uncovered intersection is the one a customer will hit on the 3rd day after shipment. The DV engineer reads the system spec, thinks like a customer, and writes a test that closes the hole. Every hole closed is a respin avoided. The third wall is the bug triage. Every morning, the DV team walks into a regression dashboard with 100 red entries on it. 100 test failures from the overnight run. Each one represents 30 to 60 minutes of investigation. The DV engineer opens the waveform, traces the failing signal back through the design hierarchy, and answers the same question every time. What broke? There are exactly 5 answers, and the cost of each one is different. 1, the RTL has a real bug, file a ticket against the design team. 2, the test bench has a bug, fix it in-house, no one else hears about it. 3, the spec is genuinely ambiguous, escalate to the architect. 4, the simulator itself has a tool bug. Open a case with Synopsys or Cadence. That case will take 3 weeks. 5, the environment broke. A server went down, a library version mismatched. The test infrastructure team needs to know. A misclassification is the silent killer of program schedules. Logging a test bench bug as an RTL bug burns a day of the design team. Logging an RTL bug as a test bench bug ships broken silicon. AI tools can cluster similar failures together. They cannot make the 5-way call. That is judgment built from 100 prior misclassifications, and the DV lead carries it. The fourth wall is the emulator decision. At some point in every program, simulation runs out of runway. A modern AI accelerator boots an operating system on the first chip. That boot takes 10 seconds of real-time on silicon. In a software simulator running at 10,000 clock cycles per second, that same boot takes 30 years. The DV team cannot wait 30 years. They move the design onto a hardware emulator. Cadence Palladium or Synopsys ZBoo. Custom FPGA arrays the size of a server rack. $10 million to buy, $2 million a year to maintain, $1 million in support contract. The DV technical lead is the person who recommends to the program manager that this purchase happens. The recommendation lands on a finance spreadsheet that already had budget pressure. The lead defends it. Cycles per second on the emulator versus cycles per second in simulation, multiplied by the number of remaining cycles the spec requires to be checked, divided by program weeks remaining. The number is the cost of not buying the emulator in calendar slip. The vendor is single source for the project lifecycle. Switching from Palladium to ZBoo mid-program is impossible. Once the purchase is signed, the lock-in is 4 years. So why is verification getting more expensive in 2027, not less, while AI tools spread across the industry? 3 reasons. Reason 1, verification is a definition problem, not a search problem. AI is very good at searching for tests that maximize a coverage metric. It is not good at defining what the metric should be. Defining the metric requires reading a Word document, finding the ambiguity, and getting an architect to commit to one interpretation. That is a meeting, not a model. Reason 2, the cost of an escaped bug has gone up, not down. A bug in a 2018 mobile chip cost a respin in 3 months. A bug in a 2027 AI accelerator costs a respin, and a customer who has already committed to a competitor's chip for next year's product window. The risk premium on every uncovered cross-coverage intersection has tripled. Reason 3, AI tools generate more tests, not fewer. Every test costs cloud compute. Every coverage point chases more compute hours. The cloud compute bill for verification on a single advanced program is now in the hundreds of millions of dollars and rising at 20 to 30% every year. So the non-obvious winner is not the DV engineer, who is still salaried. It is not even the EDA vendor on its own. It is the layer underneath the EDA tool. AWS with Synopsys Cloud and Cadence Cloud Passport running on top of it. Every time an AI verification tool launches another regression sweep, AWS bills compute hours at retail price, Synopsys and Cadence bill per token EDA usage on top, and the chip company writes the check for both. The press release reads, AI shrinks verification time. The invoice shape is exactly the opposite. The hyperscaler and the EDA tool vendor split the upside. The chip company pays it. That is the AI money flow this corner of the industry runs on. That is verification, the expensive half of designing a chip, hidden behind the design team in every press release. Real Silicon Jobs is the series that walks through the roles that actually ship silicon. Subscribe to see what each engineer does that AI is still nowhere near doing. Next episode goes inside design for test, the role that decides whether your chip can be screened on a tester in under 1 second. Watch the numbers.